In this video, we're going to draw the Valence theory diagram for the Allene molecule. Right, so this is how the Allene molecule looks like. We have 3 carbon atoms, and molecule is terminated with hydrogen atoms. There's something interesting about the arrangement of the molecule. This group, these 3 atoms, are in the plane of the whiteboard, but these 3 atoms are in a plane that is perpendicular to the whiteboard. Okay, so you can see how this molecule seems to have a twist, where those hydrogen atoms would be like this, but this one will be twisted out of the plane. Okay, so the purpose of this video is to try to see how we can come up with this geometry for the molecule within the framework of Valence theory. Right, so the first thing we do is draw the electronic configurations of the atoms, right? So we know that hydrogen is going to be a 1s, 1 electronic configuration, and then carbon is going to be the electronic configuration of helium, and then 2s2, 2p2. Okay? Now, because we have to also explain the shape around the carbon atoms, and we know that carbon is highly susceptible to undergo hybridization, we will also want to identify potentially the hybridization of the carbon atoms that you have in the molecule. Right, so we have 3 carbon atoms in the molecule. This seems to be seems to have the same shape around it as this, but that one is clearly different. Okay? In this carbon atom, you have 2 connections that seem to be 180 degrees from each other, and there is a hallmark for sp hybridization. Okay? This carbon atom has 3 connections, okay, or 3 electron groups, okay, which are planar, and the angles are approximately about 120 degrees. That is a hallmark for sp2 hybridization, okay, and that is also sp2 hybridization. Again, the electron group arrangement would be 1 group of electrons, 2 groups, 3 groups of electrons, and that signifies sp2 hybridization. Now, so with these hybridizations, what we can do is draw here with the electronic configuration for those carbon atoms in the hybrid orbital state, how those would be. Right, for the carbon that is sp, the valence electrons are going to look like this. We will have 2 sp hybrid orbitals, and then 2 unhybrid, which we're going to call the px and py. All right, so we're assuming here that is the 2pc, the one that gets hybridized. Okay, for the sp2 carbon atoms, there will be 3 hybrid sp2 orbitals. Okay, each one of these has 1 electron, 1, 2, and 3, and then we have an unhybrid p orbital. Okay, and we're not going to decide yet what is the axis of this orbital, because it can change from one carbon atom to the next. Okay, but then we're going to write 1 electron right there. Right, so with this hybrid atomic orbital structure, we're going to start to try to draw this molecule. The first thing that we do is draw the central carbon atom right here. Okay, so that will be carbon, and then that is the sp hybridized carbon atom, and then we have to draw that orbital structure. Okay, so the first sp hybrid orbital is going to be pointing towards your right. Okay, that is an sp orbital that has 1 electron. Okay, the second sp orbital points this way. Okay, also has 1 electron. Okay, so those are the 2 sp hybrid orbitals. And we still have 2 unhybrid orbitals, the natural orbitals, 2px and 2py. Okay, so I'm going to choose the 2px to be in the plane, okay, of the whiteboard and pointing up and down. Okay, there's what I'm going to be calling the 2px, and it has 1 electron. And then we'll have a 2py, which will be coming in and out of the plane. Now, that is difficult to draw in just 2 dimensions, so I'm just going to choose to write this with a different color marker, just to signify again that this orbital will be coming in and out of the plane. Okay, so this is how we're going to draw the 2py orbital with 1 electron, again coming in and out of the plane. Right, what else do we have here? All right, so we're going to start to build the molecule to the left, right here, and then we notice that there's a connection between this carbon atom and the central carbon atom. Okay, so we have to draw here that carbon atom. Now, the orbital structure is going to be sp2 hybridized carbon atoms, so there's 3 of those. which are 120 degrees from each other. That is the first one. Okay, this will be a hybrid sp2 orbital, okay, with one electron. And then we'll have two hybrid sp2 orbitals that will come in at 120 degrees. But notice that in this case what we actually want to do is express here bonding two hydrogen atoms that are coming in and out of the plane, right? So the idea is that these two sp2 hybrid orbitals that I'm about to draw, they're coming in and out of the plane, okay, a little bit. So because that's the case, I'm actually going to choose to, I can probably use a different color marker, okay, to just show that again one of these will be coming in towards the left and forwards. Okay, so this way, will be sp2 with one electron, and then the other one will be coming towards the left and inward. Okay, so that will be the other one, sp2 with one electron. Okay. And in addition to this, we still have one anhybrid orbital, okay, for this sp2, which in this case will be pointing up and down because it has to be perpendicular to the three sp2 hybrid orbitals that are in this plane. Okay, so that we can still draw as this. And again, what that means is that in this case, for the carbon atom on the left, that will be the 2px anhybrid orbital, okay, which has one electron. All right, and we'll label this as 2px. So we can then start to form here bonds. We can see that clearly one of these bonds between these two carbon atoms is a sigma overlap between an sp hybrid of the central atom and an sp2 hybrid orbital of the terminal atom. Okay, so there's a sigma overlap. And we also have that there can be a Sidon overlap, a pi overlap, between these anhybrid 2px orbitals. Okay, so that explains the double bond between those two carbon atoms. We also have to explain here those hydrogen atoms, and the idea is that those hydrogen atoms are going to be, those bonds to the hydrogen atoms are going to be just caused by sigma overlaps between the one is wave function of the hydrogen atom and one of the sp2 wave functions of the hybrid carbon atom. That's a sigma overlap. And the same thing is going to happen for the other carbon atom. One is wave function overlap with the sp2 wave function of the carbon atom, sigma. All right, so now we still have to think about the other side. And now something that is going to be the same as this terminal atom is that the hybridization is the same. So the orbital structure is the same. What is different is the orientation. Notice that in this case what we actually have is that this moiety is planar. That means is that you need a sigma orbital structure that lies in that plane. Okay, and what that's going to mean is that now you will have an anhybrid 2p orbital coming in and out of the plane. Okay, so in that case, for this carbon atom, what that means is that this anhybrid orbital is going to be in the y direction, not in the x direction, which is what we have right here. All right, so let's see how we can draw that. Right, so again, still, this carbon atom is sp2 hybridized, which means that you will have three hybrid sp2 orbitals. Okay, so that is one of them, sp2 electron. Then you will have another one at 120 degrees in the plane of the whiteboard, and another one at 120 degrees, okay, in the plane of the whiteboard, with one electron each. Okay, and we can already start to draw here how the overlaps will be with the wave functions of the hydrogen atom, 1s and then 1s. Again, what is interesting here is that these three sp2 hybrid orbitals define the plane of the whiteboard, but then you will still have 2py orbital coming in and out of the plane. Okay, and that will be singly occupied. Let's see how we can draw that then. All right, so I'm going to draw it. Again, this red marker kind of means that this orbital is coming in out of the plane. Okay, and this will have one electron, and is a 2py orbital. Right, so we're then ready to think what the connectivity with the between the carbon atoms is. Obviously, this is a head-on overlap between an sp hybrid orbital of the central carbon atom and an sp2 hybrid orbital of the terminal carbon atom. And again, because there's a head-on overlap, that is a sigma bond. Then you also have that there's a singly occupied 2py orbital and a singly occupied 2py orbital coming in and out of the plane, and those will be able to form a pi bond. Okay, so that is what your pi bond is. Okay, so this is kind of the end of the, this is the valence bond theory diagram for the Allene molecule. And again, it's very interesting because you have that, even though it looks like these bonding patterns should be the same, there's actually differences, right? In both cases, you have that this double bond is formed by a sigma and a pi overlap. But the orientation of those overlaps is different. The sigma overlap is always along the axis of the molecule. Okay, but the pi overlap in this case takes place in the plane of the whiteboard. The pi overlap in this bond takes place in the plane perpendicular to the whiteboard. Okay, part of the consequence of that is that then this CH2 moiety is in the plane of the whiteboard, and this CH2 moiety is in a plane perpendicular to the whiteboard. Okay.